So we previously learned about tangent lines, and then we learned about the definition of a limit or what is a limit. Now we're going to learn how to calculate limits using these different limit laws. So two limits, they can be added together before or after you take the limit. Same thing with subtraction. Also, anytime you multiply by a constant or even the limit itself. And same thing for division. So you could divide it before or after, as long as the denominator, the limit, is not equal to 0. I know this might look confusing, but you'll see it much better when you start solving. This is how you say it in English. The limit of a sum is the sum of the limits. That just means you can add it before or after you take the limit. Let's try one. Let's try this first one here using the limit law and this graph here in figure 1. Try to evaluate the following limits if they exist. So limit of f of x plus 5gx as x approaches negative 2. So first thing we should do is find where negative 2 is. So it's right here. This is negative 2. And f of x is this pink one here. What is the limit? Is it this open circle here or is it this pink point here? Do you remember? All right. It is where both sides, right-hand side and the left-hand side, approaches. So it is going to be 1. Actually, they have it here for me. So we're going to split it up. So it's here, it's at 1. And what about g? Where is that? That will be negative 1. So they got it there. So this part, which is this, is equal to 1. Negative 1 multiplied by 5 will be negative 5. 1 minus 5 equals negative 4. So that's pretty much how you calculate limits using limit laws. Okay, so same thing with powers. So you could take the power before you take the limit, or take the limit first and then take the power. If it is a constant, then the limit is always just that constant. So for example, if it says the limit of 5 as x approaches 9, it is still 5. Or limit of 5 as x approaches negative 1576.9, still whatever c is 5. The limit of x as x approaches a equals a. So they're mainly asking, what is x when x is going to a? Well, you already told me x is going to a, so it's a. Here, this is combining law 6 and law 8 together about the powers. So if you put a power here and a power here, the same thing, so it becomes law 9. Same thing with roots. Remember, power and roots are inverses. Okay, so here also saying that you could take the root before or after you take the limit. Let's try this one. So here, for this problem, we're breaking it up into these different sections here. So it's like 1, 2, 3. So, and then they also took the constant outside to take care of that later. Now, what if you put in 5 here, what would that become? 5 squared is 25 times 2, that would be 50. And then here, if you put 5 here, so the limit is just 5, so 5 times 3 is negative 15. And then 4, remember if it's just a constant, it's just 4. So then 50 minus 15 plus 4 is 39. They're probably mainly going to ask you which limit laws did you use. So here when we took the constant out, we took the 2 out. Let's see, which one can we take the constant out? Right here. And then, also here, that's where we took it out as well. Oh yeah, first of all, breaking it up. The adding and subtracting one, which is law 1 and law 2. See, I make mistakes too. I make lots of mistakes. And then here we used 9 and 8 to get what the limit is with the constants and the powers. That's how we solve it. Direct substitution property. If f is a polynomial or a rational function and a is in the domain of f, then the limit of f of x as x approaches a equals f of a. So this mainly means if this exists, or if a is in the domain, then you could just plug in a. This makes it super easy. You can see here it doesn't work because 1 minus 1 is 0. So you can't necessarily solve it. So x squared minus 1 and x minus 1. If I plugged in 1 right away, so 1 minus 1 and then 1 minus 1, well, the denominator is 0, so I can't do this. But why can they solve it right now? Well, if you see up here, they factored it first. Then this and this cancel. Once that cancels, you could put the 1 in place here. Put it in here because these cancel, remember? Then 1 plus 1 is 2. So if you're able to simplify something first, then you could plug it in, even if it looks like it's not going to work right away. Okay, so this is saying that if f of x and g of x are exactly the same everywhere on the function, except for at that instantaneous point A. So all the same, except for at 1. Then their limit at 1 is the same. Why does this work? Just it means that this right-hand side will be the same, left-hand side will be the same, because everything is the same besides that point. Remember, limit, we just want to know where it approaches. We don't really care what it is at that point. So if they're the same everywhere besides that point, then the limit will be the same at that point. So this theorem is what we talked about earlier. The limit is equal to L only if from the left-hand side and the right-hand side, they're both equal to L. So we have to check here, both the left-hand side and the right-hand side. What is the limit right now, okay? So here it goes to 0, this side goes to 0, so the limit is 0. So for here, we have to show that doesn't exist. Why? Because the left-hand side goes to -1, the right-hand side goes to 1. They show you in detail here how to prove it, and I want us to take a look. So sometimes you'll have an absolute value problem like this. You're going to have to break it up into two sides because remember, absolute value means one side's positive, one side's negative. So it is x when x is greater than 0, but it is negative x if x is less than 0. So since absolute value of x is equal to x for x greater than 0, we will have from the right-hand side that these are the same and is equal to 0. However, for the left-hand side, we know that here, remember this is -1, -2, and so on, right? So it is negative x. So when we look here and put it in, it will be negative x. However, this is still 0. We plug it in, it is still 0. This is 0, this is 0. The limit is 0 because both right-hand limit and left-hand limit are 0. In the next example, they're going to show you when the limit doesn't exist. So once again, we're going to have to break it up. Remember, so on the right-hand limit, the absolute value is positive, but on the left-hand limit, this side, the x is negative. So when it is positive, x divided by x is 1. But negative x divided by x is -1. So these two are different. So the limit does not exist. So this is how you prove that the limit does not exist. It is a bit confusing, but the main thing that you need to look out for is whenever you see the absolute value, then on the right-hand limit, it will be positive. Left-hand limit, it will be negative because here is negative, this side is positive. Greatest integer function, these are just step function, meaning that they're the same throughout the whole line. And at that point, it'll be 1 until 2, then it'll be 2, and then 3, and so on. So here are limit comparisons. This means that if a function is less than another function at the area near the limit a, then the limit is also less than the other limit. And squeeze theorem is if there's one function, second function, third function, and g of x is squeezed between h and f, then if the limit of f of x as x approaches a is L, and the limit of h of x as x approaches a is L, remember the lower limit, the upper limit, they'll squeeze it so that because g is always between them, that means the limit of g of x as x approaches a is also L. So higher limit right here, a lower limit here. If g is between them near where a is, then the limit of g of x will also be L. So they're actually saying it doesn't have to be the whole function. Everywhere here near A besides A, so they're just checking around this area. So even if this side g is larger or less than, it is okay. So everything near here, as long as this is true, that f of x is less than g of x, less than h of x, less than or equal to, it will be squeezed and it'll get really, really close there. And it will all be L if the upper and the lower are L. All right, that's it for 2.3.